One of the last places you would ever expect a star to survive is exactly where astronomers may have just caught one hiding. Not near a black hole, not orbiting safely far away. Inside the blinding disk of gas spiraling around one, a place we usually imagine as pure destruction. And yet, a newly identified disk transitor candidate suggests a star may be crossing that disk, briefly dimming its light in a way astronomers can actually detect. If that interpretation is right, this is not just a strange observation. It hints that supermassive black hole disks may hide an entire ecosystem of trapped stars, living out parts of their lives inside the most violent furnace in a galaxy. So, what is a disk transitor? In simple terms, it is an object passing in front of the bright accretion disk of an active galactic nucleus, or AGN, causing a temporary dip in brightness. Think of the exoplanet transit method, but scaled up into something almost absurd. Instead of a planet crossing a star may be crossing the glowing structure around a black hole with millions of solar masses. The specific idea gained traction because time domain astronomy has changed. Surveys now watch the sky over and over, looking for tiny, repeatable changes. In 2020, a team led by Barry McKernan and colleagues argued in the Astrophysical Journal that stars embedded in AGN disks could produce detectable transits. Not fantasy, a testable prediction. And that matters because AGN disks are weirdly selective environments. They are hot, dense, turbulent, and flooded with radiation. Gas drags on anything moving through it. Orbits can shrink, circularize, and align with the disk. Over time, stars near the galactic center may get captured into that flow. Once that happens, the disk stops being just a feeding structure for the black hole. It becomes a place where stars and compact objects can migrate, collide, gain mass, and possibly transform in ways we barely understand. I think this is one of the most unsettling ideas in modern astronomy. We like clean categories. Stars live here. Black holes destroy things there. But the universe keeps refusing that simplicity. The mystery begins with light curves. Astronomers looking at active galaxies sometimes see brightness changes that are too structured to dismiss as random flickering, but too unusual to slot neatly into the standard AGN chaos. A true disk transit should produce a dip with a shape, duration, and chromatic signature tied to the disk's geometry and temperature profile. That is the clue. Not just that the light changes, but how it changes. A recent candidate has drawn attention precisely because it may fit that picture. A transiting object crossing an AGN disk rather than a normal foreground event. The object is still a candidate, and that caution matters. Astronomers are not claiming victory yet. They are asking whether the dip is better explained by a star embedded in the disk, a cloud, an instrumental artifact, microlensing, or ordinary AGN variability pretending to be meaningful. This is where the story gets good, because each alternative explanation has to survive contact with the data. If the dip is caused by random disk turbulence, the event should look messy and not repeat in a coherent orbital way. If it is a dust cloud, the wavelength dependence may betray it. If it is microlensing, the light curve shape changes again. One by one, astronomers test these possibilities against timing, depth, symmetry, and color. And buried inside that detective work is the larger thesis of this video. The candidate matters less as a single odd star and more as evidence that galactic centers may host a hidden stellar population we have been conceptually overlooking. If one star can survive long enough to transit, how many others are there? How many are invisible because we are not looking for the right signature? In 2023 and 2024, AGN research kept accelerating because facilities like ZTF, Gaia, TESS, and broad spectroscopic follow-up made variability studies much more powerful. We are no longer taking occasional snapshots of these galactic cores. We are building movies, and movies reveal patterns that single images hide. Personally, that shift feels enormous. A violent nucleus stops being a static symbol of doom and becomes an active environment with weather, structure, and maybe residence. There is also a practical reason astronomers care. AGN disks have been proposed as factories for black hole mergers. In 2019, McKernan and collaborators suggested that stellar mass black holes embedded in these disks could merge efficiently, potentially contributing to the binary black hole events seen by LIGO and Virgo. If stars really are embedded there too, then the disk is not just swallowing matter. It may be assembling a whole ecological network of migration, feeding, stripping, mergers, and rebirth. So let me ask you this. Do you think the first solid proof will come from a repeating transit pattern or from spectroscopy showing a star physically interacting with the disk gas? I genuinely want your vote in the comments. Now, imagine the scale in human terms. A campfire is already hard to stare into. An AGN disk is a furnace spread across distances larger than our solar system, heated by gravity so extreme that the central engine can outshine an entire galaxy. And somewhere in that glare, a star may be trying to keep its identity. That comparison is imperfect, but it helps. This is not like surviving near a volcano. It is like trying to remain a snowflake inside a blast furnace and somehow still leaving a measurable shadow. But a star embedded in the disk would not simply sit there untouched. Gas could pile onto it. Its outer layers could be stripped. Its orbit could migrate. Its evolution might speed up or distort. Some models even suggest stars in AGN disks could grow unusually massive through accretion. A stellar life in that environment may not look like a normal stellar life at all. It may be a hybrid existence, part star, part victim, part beneficiary of the black hole's feeding structure. But this was only the beginning of the unsettling part. Because if stars can live there, they can also die there. And their deaths would not be ordinary either. Supernovae inside AGN disks could be muffled, reshaped, or amplified by surrounding gas. Compact remnants could sink deeper into the disk. Collisions become more likely. The black hole's neighborhood stops looking like empty annihilation and starts looking more like a crowded, brutal city. If that picture surprised you as much as it surprised me, leave a like, because the next piece is where this stops being just a weird transit and starts changing how we imagine galactic centers. But wait, there is a twist nobody should ignore. If we confirm even a few of these transitors, we may not just be discovering stars in black hole disks. We may be discovering that our mental image of a black hole environment has been wrong at the deepest level. Not emptier than expected, busier. That changes the question from can a star survive there to what entire population have we failed to count? And once that question appears, a lot of other mysteries suddenly look different. Why do some AGN vary in puzzling ways? Why do some merger rates seem hard to explain? Why do some galactic nuclei appear more structured than chaotic models predict? A hidden disk population could connect those dots. Confession: when I first read about this idea, I did not find it comforting or terrifying. I found it humbling. We build these dramatic stories about cosmic death zones, and then nature slips in a more complicated truth. Even beside an abyss, processes resembling community can emerge. Not peaceful community, but a system of interactions, pressures, and survival. There are hard numbers behind that possibility. Sagittarius A star, the black hole at the center of the Milky Way, has about 4 million solar masses. Many bright AGN host black holes from millions to billions of solar masses. Their disks can extend across light days to light months. In some models, embedded objects can migrate on timescales far shorter than a star's normal lifetime. And if the candidate events being discussed hold up, the transit depths can be large enough for modern surveys to catch, especially when repeated monitoring is available. A crucial detail is that the dip is not just a shadow. Different parts of the disk glow at different temperatures. The inner region is hotter and emits bluer light. Farther out, the disk is cooler and redder. So when a star crosses a specific path, it can block a very particular brightness profile. That gives astronomers a way to do something almost surreal. Map the disk by watching what disappears. And that may be the biggest payoff of all. These hidden stars are not only inhabitants, they could become probes, natural measuring tools. By tracing their transits, astronomers might infer the disk's structure, thickness, temperature gradient, and orbital dynamics in places no telescope can resolve directly. That is an extraordinary inversion. The black hole disk, which should hide everything, may reveal itself through the silhouette of a star trapped inside it. My view is that this is why the candidate matters even before confirmation. Good science is not only about answers, it is about forcing better questions. And this candidate forces a very uncomfortable one. How much of the universe have we mislabeled as sterile simply because we assumed violence and complexity could not coexist? So where does this go next? Astronomers will need more events, cleaner repeat detections, multi-wavelength follow-up, and models strong enough to separate real transit signatures from AGN noise. If a periodic signal emerges, confidence rises. If spectral fingerprints show gas interacting with a stellar atmosphere, confidence rises even more. The case will not be won by drama. It will be won by repetition. And if that happens, we may have to accept something deeply strange. In the brightest ring around a galactic monster, stars may be born into captivity, reshaped by fire, and still manage to announce themselves with a tiny dip in light across millions of light years. That, to me, is the real wonder here. Not that a black hole destroys, we already knew that. It is that even there, the universe seems unwilling to choose a single role for any place. Furnace and nursery, trap and laboratory, catastrophe and habitat, all at once. If hidden corners of the cosmos like this fascinate you, subscribe and stay with me. Because the universe keeps saving its strangest ecosystems for the places we were most certain were empty.